What if I told you that the key to understanding complex scientific concepts is hiding right inside the fantastical world of Pokémon? I'm Chukawobodo, but in this scientific safari zone, you can call me Professor Baobab. Welcome to episode 9 of Poke A Mon. Which Pokemon will enter Hooper's portal into the scientific dimension this week? Quick disclaimer, this podcast is not affiliated with the Pokemon Company, Game Freak, or Nintendo. I'm here to use the storytelling power of Pokemon to unlock the marvelous mysteries of science. Dive into Frontiers of Pokemon Research, a free ebook that reimagines your favorite Pokemon as subjects of scientific discovery. Is Pikachu's 10 million volt Thunderbolt deadly? Why is Eevee's DNA unstable? How come Mega Charizard X is blue? It's all here. Sign up for my weekly newsletter and I'll send you this exclusive journal to spark your imagination and ignite your curiosity. Don't miss your passport to a world where science and fiction collide. What's up, Science Squad? Professor Baobab here. And if you've ever wondered how a tiny yellow mouse could potentially light up an entire city, you're in for a ride. Look, I've spent years in labs, diving into the weirdest corners of scientific research. I've seen things that would make your high school physics teacher's head spin. But nothing, and I mean nothing, gets me more fired up than the intersection of physics, chemistry, and, you guessed it, Pokemon. Today's episode is all about electricity. But wait, there's more. This isn't your typical boring textbook electricity. We're going to explore the kind of electrical magic that happens inside living, breathing organisms such as Pikachu. You will never see Pikachu in the same way after you listen to this full episode. You have been warned. Pikachu isn't just a cute character and the mascot of the world's most grossing media franchise. It's a blueprint for understanding how electricity works in nature. Let's get charged up. I'm about to turn what you thought you knew about electricity on its head. I'm going to explain the science of electricity first. Then I'll explain whether the Pokédex entries about Pikachu are scientifically plausible or just Game Freak's creativity in action. What is electricity? Which force is so powerful it can light up entire cities, yet so delicate it can transmit the tiniest signals through your nervous system? Electricity is the flow of electric charge, typically carried by particles called electrons. I say typically because electrons are not the only charge carriers that can move. Electrons are negatively charged particles that can move through a conductor, like copper wire, to create an electric current. You may already be familiar with two forms of electricity: static electricity and current electricity, which we just refer to as electricity. Static electricity is the buildup of electric charge on a surface, often caused by friction. A classic example is rubbing a balloon on your hair. The friction transfers electrons, leaving one object negatively charged and the other positively charged. This imbalance creates a small electric field, which you can sometimes feel or even see as a tiny spark. Current electricity, on the other hand, is what powers our world. It's the continuous flow of electrons through a conductor, driven by a potential difference or voltage. Think of it like water flowing through a pipe. The voltage is the pressure pushing the water, and the current is the flow itself. But electricity doesn't just flow aimlessly, it requires a closed circuit, a complete loop allowing electrons to return to their source. Without this loop, the flow stops. This principle powers the electronic devices you use daily, from your smartphone to your coffee machine to your refrigerator. One of the most awe-inspiring phenomena in nature is lightning. Lightning is a colossal example of static electricity in action. When little pieces of dust or ice in clouds rub against each other in the sky, they create a charge imbalance. The resulting discharge of energy seeks equilibrium or balance by jumping to the ground or another cloud, producing a brilliant flash of light and a spectacular roar called thunder. Now, what exactly is charge? In physics, charge is a fundamental property of matter, much like mass. It determines how particles interact with one another through the electromagnetic force, which is one of the four fundamental forces of nature. There are two types of charge, positive and negative. Opposite charges attract, while like charges repel, which is probably the easiest idea to remember about charges. The carriers of charge are namely the subatomic particles, protons, and electrons. Protons, found in the nucleus of all atoms, carry a positive charge, while electrons, which orbit the nucleus, carry a negative charge. When these charges move, they give rise to electricity. This brings us neatly to the concept of current. Electric current is the flow of electric charge through a medium. In most cases, this charge is carried by electrons. Picture a crowded hallway in which people, all of whom represent electrons, move in one direction. That collective motion is analogous to electric current. The strength of this current is measured in amperes, or simply amps, named after André Marie Ampere. 1 amp equals the flow of about 6.24 quintillion electrons passing through a point in a circuit every second. 6 billion might seem a lot, but electrons are so small that you wouldn't be able to see them with your eye, even if you could cram them all into a ball, as the ball would still only be about 10 nanometers wide. I think it's amazing that something so puny can power our entire modern world. Currents represent a flow of electrons or other moving charges, but what causes them to move in the first place? There must be some kind of driving force. There is, and this force, called voltage, acts like the pressure in a water pipe, pushing electrons along a conductive path. Without voltage, there's no movement, no energy transfer, and no electricity. Voltage, also known as potential difference, is the force that pushes charged particles through a circuit. It's what transforms static charges, particles sitting idly on a surface, into dynamic currents capable of powering devices or perhaps unleashing a Pokémon's thunderbolt attack. To understand voltage, consider also the following illustration. Imagine a hill with a stream of water flowing downhill. The height of the hill represents the voltage, while the water represents the current. The steeper the hill, the more forcefully the water flows. Similarly, a higher voltage means a stronger push on the electrons, driving them through a conductor. Voltage is measured in volts, named after Alessandro Volta, the inventor of the electric battery. A single volt is defined as the potential difference that drives 1 ampere of current through a resistor of 1 ohm. I know, that might sound abstract, and we're getting to resistance in a moment. But it's essentially a measure of how much energy each electron carries as it moves through the circuit. For reference, the voltage of a typical household battery is around 1.5 volts, while the outlets in your home operate at around 230 volts here in the UK. Now imagine the incredible energy required for lightning, where voltages can soar into the millions. Find out in my free ebook how Pikachu's 10 million volt thunderbolt might not be as deadly as you think. Resistance is the opposition to the flow of electric current. It's the electrical equivalent of friction. Imagine water flowing downhill again. Only this time, there are huge rocks in the stream that cause some of the water to spill onto the grass. The rocks slow the flow of water, making it harder for it to pass. In electricity, resistance works the same way, hindering the movement of electrons through a material. Resistance is measured in ohms, named after the German physicist Georg Ohm, who formulated Ohm's law. This law states that the current, I, through a conductor is directly proportional to the voltage, V, and inversely proportional to the resistance, R. Mathematically, it's expressed as V equals IR. This simple equation explains how voltage, current, and resistance interact. For a given voltage, higher resistance means less current flows, and vice versa. The level of resistance in a material depends on several factors, including its composition, temperature, and size. Metals like copper and silver are excellent conductors because they have low resistance, allowing electrons to move freely. On the other hand, materials like rubber and glass have high resistance, making them bad conductors or good insulators. However, resistance isn't just about slowing the movement of charged particles, as it also dissipates energy, often in the form of heat, so-called Joule heating. This is why electrical wires can warm up when a high current flows through them. Resistance plays a crucial role in the design of electrical systems, ensuring they operate safely and efficiently. Now let's talk about Pikachu. I'm going to state the Pokédex entry and which game or games it belongs to. I will then analyze it. Finally, I will render my verdict, deciding whether or not the entry is logical or scientific. The Pokédex entry from Pokémon Red and Blue states, when several of these Pokémon gather, their electricity could build and cause lightning storms. This description suggests that Pikachu collectively generate enough electrical energy to influence the atmosphere and create lightning. Scientifically, this resembles a phenomenon known as atmospheric ionization. Atmospheric ionization is the process where atoms or molecules in the atmosphere gain or lose electrons, creating charged particles known as ions. Lightning forms when charged particles within clouds create a potential difference, resulting in a massive discharge of electricity. For this to happen, a group of Pikachu would need to produce and release significant amounts of charge into the air. However, generating a charge imbalance on this scale would be extraordinarily challenging for biological organisms. Even with specialized structures like electric sacks, the energy required to ionize air and trigger lightning far exceeds what any known animal or group of animals can produce. In nature, even electric eels, which can deliver shocks of up to 860 volts, are far from achieving this level of electric output. Remember, lightning strikes are on the order of millions of volts. Verdict: while plausible in concept, the energy requirements make this an extreme exaggeration of Pikachu's abilities. The Pokédex entries from Pokémon Platinum, Black, White, Black 2 and White 2 states it occasionally uses an electric shock to recharge a fellow Pikachu that is in a weakened state. This entry hints at Pikachu transferring electrical energy to aid another Pikachu. In the real world, this could be compared to defibrillation, where electrical energy is used to restart or stabilize a heartbeat. Pikachu's electric sacks might allow it to store and release small bursts of charge, akin to a biological capacitor. However, recharging another organism would require precise control over voltage and current. If the delivered shock is too weak, it wouldn't be effective. If it's too strong, it could cause harm. Additionally, a biological system that repeatedly discharges electricity would need a highly efficient mechanism for regenerating its energy reserves, likely through metabolic processes, but this could be regenerated while sleeping, as we will soon see. This isn't entirely out of the realm of possibility. Some animals, like electric rays, have so-called electric organs capable of generating electric fields, but the precision and intent implied here would be a groundbreaking feature in the animal kingdom. Verdict: surprisingly plausible, though it would require incredible precision and energy efficiency. The Pokédex entry from Pokémon Fire Red and Y states, it has small electric sacs on both its cheeks. If threatened, it looses electric charges from the sacs. This description is perhaps the most realistic of the three I've mentioned so far. Pikachu's electric sacs could function as specialized organs for storing electrical energy. Similar to the electric organs of electric eels and rays, these sacs might consist of stacked electrocytes, which are cells capable of generating voltage when stimulated. When threatened, Pikachu could activate these electrocytes to release a burst of charge, creating a defensive shock. In nature, electric eels use a similar mechanism to stun prey or deter predators. The challenge for Pikachu would lie in maintaining its energy reserves and ensuring it doesn't deplete them too quickly. This would require a highly efficient metabolic system to regenerate electrical energy between discharges. Verdict: very plausible, with strong parallels to real-world electric animals. The Pokédex entry from Pokémon Sun states, a plan was recently announced to gather many Pikachu and make an electric power plant. This entry envisions Pikachu as a renewable energy source, harnessing their electrical abilities to power a facility. At first glance, this seems comparable to how humans use electric eels in controlled environments to power small devices, as a demonstration of bioelectricity. Lightning bolts release about 1 billion joules in a single strike. That's roughly enough to keep the lights on in every single home in the UK, albeit only for a fraction of a second. However, Pikachu can sustain Thunderbolt for hundreds of times longer than a fraction of a second. In my video on Pikachu, which you can watch by following the YouTube link in the show notes, I calculated that a power plant would need to constantly drain the power from at least 10,000 Pikachu to power the UK. Ordinarily, real-world electric animals like eels generate brief bursts of energy, not the sustained output required for large-scale electricity generation. Furthermore, the metabolic cost to Pikachu would be immense. Constantly generating electricity for a power plant could deplete their long-term energy reserves, potentially harming their health. From a technical perspective, managing the variability in electrical output from multiple biological sources would require complex systems to stabilize and store the energy. While it's a cunning concept, the inefficiencies and the ethical concerns surrounding the use of living organisms for large-scale energy production make this scenario unlikely in reality. Verdict: imaginative, but logistically and ethically implausible. The Pokédex entry from Pokémon Moon states, "It's in its nature to store electricity. It feels stressed now and then if it's unable to fully discharge the electricity." This entry suggests that Pikachu naturally accumulates electrical energy and experiences stress if it cannot release it. Electrolytes are similar to capacitors in that they can be charged and discharged, whereas a rechargeable battery works by a reversible chemical reaction. A capacitor works by storing electrical energy in an electrostatic field between its plates. Incidentally, a capacitor works by maintaining a voltage between the plates. However, there is an air gap which prevents the charges from moving because the resistance of the air is too high, so an electrostatic field is generated. In Pikachu's case, prolonged storage without discharge might cause physical stress due to increased voltage and the potential for internal overheating thanks to Joule heating. In real-world systems, capacitors must release their charge periodically to prevent damage or inefficiency. Similarly, Pikachu might rely on frequent discharges to maintain its health and comfort. Verdict: highly plausible, as capacitors are very similar. Finally, the Pokédex entry from Pokémon Sword states, Pikachu that can generate powerful electricity have cheek sacs that are extra soft and super stretchy. Here we're introduced to a fascinating physiological detail: the relationship between the structure of Pikachu's cheek sacs and its electrical capabilities. This suggests that the softness and elasticity of the sacs might enhance their ability to store and discharge electricity. It might be that cheek sacs become soft after having been used consistently. Biologically, this could be explained if the sacs are composed of highly specialized elastic tissue that can expand to accommodate large quantities of charge or a great number of electrocytes. Elasticity might also protect the sacs from damage during rapid discharges, distributing the stress evenly across their surface. Most likely, their skin is much more elastic than ours. This structural adaptation would allow some Pikachu to generate stronger electrical attacks while maintaining their physical integrity. In the natural world, we see similar principles in organisms with specialized storage organs, such as electric rays. Their electrical organs are adapted to handle repeated discharges without suffering damage, thanks to their robust and specialized cellular structures. Pikachu's stretchy cheek sacs may serve a similar purpose tailored for its electrical needs. Verdict: scientifically plausible, offering a logical explanation for enhanced electrical output. You know what's wild? It's not just a Pikachu you find in tall grass. No, because we didn't just learn about electricity today. I changed how you think about science. If you want to see how science and Pikachu can come together in different ways, don't forget to get your free ebook. So, next time you see a Pikachu, I want you to remember that little yellow electric mouse isn't just a character. It's a living, breathing, scientific hypothesis waiting to be unpacked. Science Challenge! Before our next episode, I want you to do something crazy. Find one thing you think you don't understand in the world. Just one. And ask yourself, what Pokemon could be used to explain this? Email me your findings and I might call out your name in the next episode. My email address is Charlie Hotel Uniform Kilo Alpha 1000@hotmail.co.uk. It's also in the show notes. What did you think? Isn't the power of science simply amazing?